Good morning, Calculus 2 students. Every time Internet Explorer does an update, they do all kinds of weird things to my Zoom software, and so I have to go through all the hoops to get everything turned back on. I sometimes cringe every time I turn off my computer and it says, "Oh, update," and turn off or update and stay on, and I do this and say, "Okay, here we go again." Well, I hope everyone's doing well today. Let me just remind you that next week we're trying to space the test a little bit closer together so that you don't have so much content on one test. So at the end of this week, I'll have up another announcement that will apprise you of what we will have for test number 3. Again, the focus is to allow you to test with a little bit more level of comfort, and also that the amount of material maybe is not so huge that you feel just inundated. I know you have lots of other classes, and so I want you to lower stress and lower anxiety, and I appreciate your hard work. So what we want to do today, and also let me remind you, you've got that signature assignment. And that's probably the last thing that you even want to think about, but it's a very straightforward exercise using the topics from chapter 7. So you will not find it to be unnecessarily difficult. So go ahead and work on that and get that turned in. It'll count as a quiz grade. So like I say before, it's something that's worth your while. And these assessments, you have done in other classes, and it's part of the uh, Southern Association accreditation process that we do at the college. The accreditation process is what makes our school legitimate. And any school that has the Southern Association accreditation is a well-respected school of higher learning. So that's part of the process that we do. And we've always been honored in a lot of ways for that particular signature assessment that we do. So thank you for agreeing to do that and helping us maintain good standards at the school. Now, what I want to do is start with sequences and share with you just some preliminary information, and then going through some examples and some basic theorems so we can start talking about infinite series. So let me share my screen. Now, what I wanted to do was just give you a couple of simple uh, preliminary ideas having to do with sequences. And let me get just a little bit more light on this, if that'll help a little bit, and then do a focus. Okay, let me move this over here. I've got to move Professor Ron out of the way. There we go, and get rid of all these uh, lines. Here we go. There we go. And I also talked to Xfinity. I told him, I said, my speed on my internet is slowed down a little bit. So I gave him a little bit more money, and hopefully it won't glitch like it has been doing. I guess money solves everything eventually. Now, the sequence is something that you have dealt with in previous classes many times. And so you really intuitively already know about a sequence. And basically in pre-calculus, a sequence was defined. So when I teach my pre-calculus, I define it just like I'm doing here, but that's been a while. So let's just remind ourselves, a real sequence is a function f, and we write a function from the natural numbers into the real numbers, defined by the following. That is, we're going to say f of n, where the input is a natural number, is a real number output a sub n. And so this type of notation is what we like to use with sequences. F of 2 would be fine, but the a sub 2 is actually a better choice of symbols because we can see that a sequence is an ordered list, and it's ordered by the natural numbers. So you have a first element, a second element, a third element, just like we've written here. So instead of saying f of 1, we will usually just say a sub 1 using the subscript. Likewise, a sub 2 will be the second element of the sequence, f of 2. And then, of course, we can move to what we call the so-called general term, a sub n. Now, you're thinking, well, do we write the sequence as a set, of elements, infinite elements? For instance, you could think of a sequence in terms of the curly braces, an a sub n, where n goes from 1 to infinity. And that's fine, but usually we're pretty lazy, and we'll just represent a sequence by the general term. For instance, I'll say, suppose we have a sequence a sub n, and that will basically be representing all of these symbols here. In mathematics, we choose to go with a less busy symbolism as long as everybody agrees with it. And this is standard. So we want to think this, but usually we will just write this to stand for a sequence, like we'll just say a function is f of x and keep it at that. Now, we discuss limits of sequences, and just like we have limits of functions, well, a sequence is a function. So we can also talk about what it means for a sequence to have a limit. Now, this should remind you, in this particular case, of the limit at infinity. So for instance, what we're seeing here is as n tends to infinity, do the function values actually converge to a real number? Okay, so we're not talking about x approaching, or n approaching 3 or n approaching -2 from the right or something like that. We're talking about a bona fide limit at infinity, where you might think about horizontal asymptotes from pre-calculus. I mean, we're going to talk about that today, just as we remind ourselves about what we've done before. So what we can do, at least formally for a limit, we will fix a real number L, and we'll let a sub n, like I said before, be a sequence. Then we're going to say that the actual limit of a sub n is n tends to infinity is L. That is, the sequence has a limit if and only if, for every positive epsilon, there exists an n. That is, we can go far enough out in the sequence so that the actual term of the sequence is within epsilon of L. And what a lot of students think of is this is like a little epsilon channel about L. And once you get far enough out in the sequence, all of the terms reside in that channel. So again, think about it this way, like a horizontal asymptote in pre-cal or cal 1. We want to say that there'll be a cutoff point specifically. And then you're thinking, does this need to be strict? Well, sometimes we might have it relaxed a little bit, greater than or equal to. But that's not a problem. For instance, if we have maybe strictly greater than 10,000, we can just say n is greater than or equal to 10,001 or whatever. So this can be relaxed. Basically, it just says there is a point at which the terms of the sequence are close to L, and close provided the particular tolerance that we have here. So for instance, if you gave me an epsilon of 1, we should be able to figure out an n. And then of course, if you give me a smaller epsilon, it stands to reason that the n would necessarily be larger. So again, this basically works just like the limits you had in calculus 1. So again, nothing abstract here, very straightforward arithmetic. Now what I want to do are just some simple examples of some sequences, and then talk about some of the theorems that follow from the definition of the sequence. So let's just do some simple examples. So here's the first one. So in this particular case, I just want to look at a sequence that is defined by a general term. Let me adjust my document cam a little bit. There we go. Excellent. Okay, good. So we have cosine n pi over 2. So this is a nice trig function. We understand trig functions. And first, what we can say is that, well, this sequence is bounded. We know the cosine function is bounded. So first, we can observe in this particular case that all of the terms would lie between -1 and 1. That's just a basic property of the cosine function, especially when you start with the unit circle and define the cosine of t, the distance along the unit circle there as an input, to be the x-coordinate of the terminal point. So again, this goes back to what you did initially in your trig classes. And then you think, okay, well, let's just write down some elements of this. You might look at this and think, well, I wouldn't think it would converge, Professor Ron, and you would be correct. But let's look at some terms. So we're going to start with 1. So we'll have cosine. So we have 1 times pi, so that's just pi over 2. And cosine of pi over 2 is 0. So we're just going to write down several elements and see if we can find some patterns. So a sub 2 will be cosine 2 pi over 2, which is cosine of pi, which is -1. Very simple, but you'd be surprised how often we make careless mistakes with simple trig functions. Then we'll have cosine 3 pi over 2. N is equal to 3. And of course, that's on the axis. Let me do one more adjustment here with the sunshine. Bring it down just a little bit. There we go. I don't want it to be so flush that you can't see. And of course, that's a 0. And then a sub 4. We'll have cosine of 4 pi over 2, which is cosine of 2 pi. And of course, that equals 1. We're back around to the point 1, 0 on the unit circle. A sub 5 cosine 5 pi over 2. Well, that's just cosine of pi over 2, which is 0. And then a sub 6 cosine 6 pi over 2, which is cosine of 3 pi, and that just takes us back around to pi. So that's a -1. Let me just do one more, or 2 more if you like. And then we'll have, so we've got 6 and we'll do 7. Now when we do 7 pi over 2, that's just, that again, that's back to 3 pi over 2 because we've got a multiple of 2 pi in that, and that's 0. And then to 8. So that'll be cosine of 4 pi, which is back around to 1, 0. So we get 1, etc. So this is not a surprise here. Notice that we've got this one, we've got this 0 occurring. Let's just mark that off. And we see that when we have, in this particular case, an odd multiple of pi, for instance, we could say a sub 2n minus 1, where n is an integer. This would just be, and I'm not trying to make, could change the letter, but this will be the input, so to speak. This will be cosine of 2n minus 1 pi divided by 2. And here we're taking n to be greater than or equal to 1. And then, of course, this will just be odd multiples of pi over 2. Pi over 2 3 times pi over 2, 5 times pi over 2, 7 times pi over 2. These are all 0. Okay, so that's established. And then we can look at some other ones. Let's say this -1 here. And then we have another -1. And what we're seeing in this particular case is that, and I would say that how does this impact what we're doing? For instance, we're thinking, okay, so we've got a multiple of pi here, a single multiple, and here we have 3, and then of course the next one would be like a 5, etc. So we're thinking, okay, so let's again do an odd multiple. Now, when we think of odd multiples of pi, we think of what we have here. So we'll say n greater than or equal to 1, and we'll have, let's see here, let me just write what I want to have in here. So we'll think of this way. So we want to get a 1 and then a 3. And so let's see here, we've got like 4n plus a 2. So this would be, let's see, so we have 4n plus 2 pi over 2. And we can factor, so we have cosine 2n plus 1 divided by 2 pi. And of course the 2's absorb. And so we have cosine of 2n plus 1 over 2 pi. Now, if I look at this, I actually would have to stretch this a little bit. I will actually start at 0 because I want to be able to get pi out of this. But, oh, excuse me, of course, the 2's absorb. That would be kind of a mess. You don't need the fraction bar. So now when we look at this, we're thinking, all right, okay, so here's another subsequence. If we have inputs that look like this, 4n plus 2, then when we substitute the 4n plus 2 in for n, we divide by 2, then we factor the 2, and that will give us a 2n plus 1 times pi, which gives us, and if we start with 0, that'll give us pi, 3 pi, 5 pi, 7 pi, and when we think about all of those are always on the x-axis at the point -1, 0. So these will always be -1. So we have to be a little bit more clever about the subscripts here. And then of course, what's the other one? I think we've got a 1. So let's put a box around this, 1. So now we want to end up at 0 and 2 pi, 4 pi, things like that. So let's first think of a sub 4n, see if this will work. Cosine 4n pi divided by 2, which will be cosine, so the 2's absorb, and we just get, in this case, 2n pi, or cosine, well, that'll be fine. That'll just be even multiples of pi, and that'll be fine. And that'll give us 1. And in this case, we can notice here, we can always be flexible here. We could start at 0 to pull in cosine of 0 if you like. But if you don't like that, we can just start at 1. It doesn't matter. The idea here is that it pretty much we're starting at 1, and since we did this, I'll just have this at 1. This will actually cover pi, which is that one, which is a sub 2. So now when you look at this, we're thinking, okay, well, we've got odd numbers here, 1, 3, 5, 7, like that. So basically, let's just kind of say this will be 1, 3, 5, 7, etc. And then the subscripts here will be 2, and then we go to a 6, and then a 10. So separated by 4, 2, 6, 10, 14. And then here we start out, we get 4. So 4, 8, and then we have 12, and then 16, etc. Just separated by 4s. Now, when we look at this, we see 1, 2, 3, 4, 5, 6, 7, 8, and then there's a 9. So we cover all the natural numbers. And you're thinking, well, Professor Ron, you certainly are doing a lot of detail with this. Well, here's the deal, ladies and gentlemen. You can't always just say, oh, well, it doesn't have a limit, I don't care about it. You really have to look at a sequence to then think, well, can I use a technique from Cal 1 and boom, I'll just pass to the limit? Possibly. Or maybe it doesn't really look like it has a limit, so I need to investigate. So when we investigate, we see that we have subsequences that do have limits. This did not happen by chance. What we see here is that when we use these subscripts, 1, 3, 5, 7, which we can generate this way, we get an output of 0. We get a constant sequence. So here's for instance, this is the constant subsequence 0. So we get 0, 0, 0, etc. So we get constant subsequences. This is a nice example. And then here we get another constant subsequence. It's just negative 1s, negative 1, negative 1, negative 1, negative 1, etc. And then here we get another constant subsequence, 1, 1, 1, 1, etc. Now, again, your work in Calculus 1 would say that each of these subsequences has a limit. The limit of this sequence is clearly 0. The limit of this sequence is clearly negative 1, and the limit of this sequence is clearly what? Positive 1. So we could say something like this. The limit, and we'll write this in the abstract, of a sub 2n minus 1 as n tends to infinity, from this case is 0. The limit as n tends to infinity of a sub 4n plus 2 equals negative 1. And the limit as n tends to infinity of a sub 4n, where we have this definition of the general term with these subscripts, is 1. So we get 3 convergent subsequences. Why is that true? That is a theorem in mathematics. And it's easy to state. An infinite bounded sequence has at least one limit point. And the limit point, this one has 3. So this is called the Bolzano-Weierstrass. And the Weierstrass is the same person that came up with the trigonometric substitution when we have rational expressions of sine and cosine to integrate. So Bolzano-Weierstrass. And infinite bounded. And when you get to advanced calculus, you can prove this. We could prove it now, but that's going to come later. An infinite bounded sequence, in this case, and we'll just say of real numbers, we can stick to that. We'll make it, but it doesn't have to be. But since we're talking about real numbers, we'll say of real numbers. They could be complex, has at least one limit point. So the idea here is even though there is no limit, because when we look at this, we would say that the limit of cosine n pi over 2 as n tends to infinity does not exist. And you'd say, well, it diverges by oscillation, so to speak, because it really can't decide what the limit is. It's jumping between 0, -1, and 1. But the Bolzano theorem says that if you actually have a bounded, and that's why I made this observation at the front. You're thinking, well, what is he doing here? I don't care about this. Well, again, the idea in this particular case is that even though we fail to have a sequential limit in the general sense, we do have what we call subsequential limits. That is, the subsequences have limits. And again, that is a direct consequence of the Bolzano-Weierstrass theorem. Again, this is not just something that happened by chance. There's going to be at least one, and you'll be able to prove that if you take more math. And again, the ideas are arithmetic. So what I want to show you here is that when you have a sequence, it's just like looking at a function, and you have to investigate a little bit. So when you don't have a limit, WebAssign might just want you to say does not exist, and that's fine. But I want you to be aware of the fact that subsequential limits will exist. Now, of course, if this is not true, you still could have a subsequential limit. It, however, is not guaranteed. So when you got the sines and the cosines, you know you're going to have at least one, and you can bank on it. So you could tell your colleagues, okay, this is going to have a subsequential limit, and you won't tell them why. You'll just say, and then they'll have to figure it out. Okay, now there are a couple of examples that I want to talk about here, and this is what I was just saying. Now, this is where we get to use our calculus 1 and be lazy, and we all love to be lazy. So these are in your notes that you have on Blackboard, but I always take the opportunity to rewrite things and look at things just to kind of maybe present them a little bit differently, but essentially the same. And what I wanted to do was make you aware that you can already compute a bunch of sequential limits. So we're going to think about a limit at infinity. Suppose f of x is a real valued function of a real variable, and L is an element of R fixed. When I say fixed, we could say X is a real number, but it's not necessarily fixed. So when I'm fixing it, I'm making it a constant. So that's a phrase that's used a lot in mathematics. Such that as X passes to infinity, F has the limit L. Now, here's what's wonderful about this. You already have a ton of limits that you can compute. Remember L'Hopital's rule? We're going to be able to use L'Hopital's rule with sequences, and you're thinking, hallelujah, I like L'Hopital's rule. It's easy. So we say, define the sequence where we restrict to the natural numbers. So we take this function f and we only evaluate it at natural numbers. But here's the thing. It doesn't matter if we just kind of pick every natural number. We know that this function converges to L. So if we only pass through the natural numbers, we still get the same limit. So if you want to think, well, back in Cal 1, if I changed all the n's to x's and make it look like a Cal 1 problem, I'd get this limit. Well, then you're done. So what I have written here are some real simple examples just to kind of show you. And then you're thinking, do you always have to go back to a real variable? Will I be cheating otherwise? Well, occasionally it's nice to think of the real function. We'll have opportunity to do that in this chapter, but it certainly wouldn't be a problem if you stay with the n. It's just that theoretically you're utilizing a a result that requires that there not be any holes. You know, with the natural numbers, you got big old holes between 1 and 2, whereas with the real line, it's a continuum. So here's an example that we know from Calculus 1 and pre-cal when we study interest. Well, the limit as x tends to infinity of 1 plus 1 over x to the x is the natural base. We'll just go ahead and make a sequence out of it. Okay, boom, done. Okay, well, what about when we were doing horizontal asymptotes? And the degree upstairs was the same as the degree downstairs. And you said, oh, we take the ratio of leading coefficients. Exactly. We'll just switch it to a sequence. Replace the x's with n's and only run through the natural numbers. You got a limit. So what you already have is amazingly simple. I mean, you remember this was your bread and butter with the rational functions. And any power of this, any real power of x that's positive, 1 over that also goes to 0. We'll just make a sequence out of it, 1 over n. And like 1 over n squared, that goes to 0 too. It's the same kind of ideas going on. Now, of course, remember our special limit? Well, for instance, we know that the argument of sine and the denominator must tend to 0. So we flip it around. We just say, okay, let x pass to infinity and then create arguments 1 over x which go to 0. This we'll use later on. Okay, well, this is 1 because that's basically sine of 0 divided by 0, which we proved in Cal 1. We'll just make a sequence out of it. So the limit as n tends to infinity of sine of 1 over n divided by 1 over n is also 1. So this result here is a major result that gives us plenty of sequential limits. So we don't have to learn anything new. And then, of course, if we need, like here, we would need L'Hopital's rule and take logarithms, or we could use a technique from Cal 1 that didn't use logarithms when we didn't know much. But the idea here is that all of the theory that you studied about limits at infinity is now applicable to the sequences. Now, here's one thing that's that you need to be careful of. This kind of harkens back to the first one, and I kind of used it as an example. Okay, what did I write here? Repeat after me. The converse is not true. So at home you say, yes, Professor Ron, the converse is not true. Well, how can we say that? Well, we just need a counterexample. Well, here's a prime example from the last problem that we did. If we just consider the sequence where we've got arguments that are basically that are exactly odd powers of pi, 3 pi, 5 pi, 7 pi, 9, etc. We know the outcome is -1. That's a good one. I mean, this we would have to analyze like we did previously. That was one of the subsequences. Okay, well, now let's just go to the real valued function, go from here to the real valued and replace n with x. And then we're no good deal, no deal. Because now this is a bounded function, but it's going to run between -1 and 1. Notice here, when you factor this, just like you did in pre-cal, the k is 2 pi, so the new period is 1. And so as you go from 0 to 1, the cosine is going to run from +1 to -1. Then go 1 to 2, +1, -1. And then 2 to 3, +1, -1. So that will oscillate between -1 and 1. So the converse is not true. You can't say, well, I've got a sequential limit, boom, I have the real limit. That doesn't work. And here's your counterexample. So as long as you're starting with a real valued limit of a real valued function, then you're fine. You can go directly to the sequence and have a bona fide limit, and you don't have any more work to do. So just be careful that you don't go in this direction. Remember, the converse is not true. This is Folks, what we're doing now is called real analysis. This isn't just plug and chug. You know, you can't use your fancy computer algebra systems to do your integrals and things. I mean, here like you do. And I wish you wouldn't do it. I know some of you do, but that's okay. Uh, it is what it is. But here, you actually have to work it out. I mean, when there is a limit, fine, but when there isn't a limit, you have to do a little bit of work. It's like doing a word problem. Now, you're thinking, okay, Professor Ron, and I just want to go through this. These are real simple. There are a lot of results that we won't have time to prove rigorously, but we will be able to justify them with good examples. And this next theorem that I want to state for you, and if we have time, we'll go through some of these. These are properties of limits, just like you had properties of real valued limits of real value functions back in Cal 1. So I just wanted to kind of run over these to show you that they're essentially the same. All of those processes that we did get moved right into the sequence theory. So we don't really have anything new to learn. It's just now that we're talking about limits at infinity. So now if we have two sequences that have limits, that is the limit of sequence A is L, and the limit of sequence B, in this case B sub n is K, and then we have some fixed real number C. Well, everything that you did in Cal 1, this same theorem applies to sequences. In analysis, you actually do sequences first, then real value functions. So it's flipped. So just like we had before, the limit of a sum or a difference is the sum or difference of limits. Just like you had in Cal 1, the proofs are essentially the same, the limit at infinity proofs, which you should have done in Calculus 1. And then, of course, if we multiply a sequence by a fixed real number, we just multiply the limit by that number. So again, basically you're factoring the constants, you do the computation, and then boom, multiply the result that you get by the fixed real number. So again, you can factor constants. And then, of course, you know, I mean, if one of the limits is already zero, the result is zero. But when L and K are non-zero, this is a very useful result. That is, if you take the limit of a product, you get the product of limits. And that proof is the same. But again, that's a little bit more arithmetic, especially if you remember from Cal 1, that required a little bit more work with the triangle inequality, but still a very nice result. Of course, it didn't work that way with derivatives, right? And now, of course, if K is a non-zero limit, and we'll just say L2 for this to even be interesting, otherwise we just have zero. So when we have non-zero set up going here with the limits, the limit of the quotient is the quotient of limits. So all of the nice theories that you utilized in Cal 1 with these properties are now applicable to sequences. So that's a good thing. We're good to go with that. Now, I wanted to share with you some results that follow from this and keep everything in order. And we'll use this. I'm getting a little cover here. The next two results are these. And one is just the squeeze theorem that you have from Cal 1, and others the absolute value theorem. They're easy to prove. So you just actually use the same result from Cal 1. Now the squeeze theorem, just to remind you about that, we fix an L, a real number, and we have three sequences, okay? So here's what we have: A sub n, B sub n, and C sub n. And we have that the limit of the sequence A sub n and B sub n coincide. It's L. And in addition, eventually, there is some cutoff in the natural numbers such that we get this compound inequality. That is, C sub n is squeezed between A sub n and B sub n. And back in the dark ages, when Professor Rahn was at Carolina, we called this the sandwich theorem. That's what Swakowski, I told you that was the calculus book I used for Marquette University. And he termed it the sandwich theorem. So it's the same thing. So we sandwich C sub n between A sub n and B sub n, or squeeze it. And the result of this is that when you pass to the limit of C sub n must also be L. There's nowhere for it to wiggle out. I mean, it's stuck between A sub n and B sub n, and their limits are both L as n passes to infinity. So again, the same result that you used in Cal 1. So again, a very nice result that is extremely useful. Now, one result that we really didn't have that actually utilizes the squeeze theorem is called the absolute value theorem. And let me tell you about that. I want to say a little bit more about this. Say we have a sequence A sub n, okay, and you're thinking, you know, maybe this might be a sequence that would have positive and negative outputs like the very beginning one that we did. And when we look at the sequence of absolute values, that is, we analyze that and we get limit 0. Well, then we can conclude that in this case, that the limit of A sub n is also 0. Now, I want to say a little bit about that. Now, when you think about these examples and you think about what we're doing, it's not at all surprising, for instance, that we get results that are very similar to what we've already done. So if we look at this, we're thinking, okay, we've got this sequence A sub n. Well, I'm just going to write this. I don't want you to see that example yet. So I'm just going to say, why is this true? And so you look at this and say, okay, well, let's see, we have a sequence, we know this is true, and then we can say, well, what do we know about absolute value? Well, observe the following. That is, we can always bound A sub n, and you're thinking this is like, you know, obvious, Professor Rahn, but sometimes the obvious observations get us where we want to go. So we can always sandwich A sub n. It's going to be equal to one of these for each n. That is, we can take the absolute value of A, which is non-negative, and that's always going to be an upper bound. And then, of course, we can take the negative of the absolute value, which is less than 0 or possibly equal to 0, which will always be a lower bound, okay? So you're thinking, well, okay, and you'll say like, where n, in this case, is greater than or equal to 1. So you might say this is obvious, but this is property of absolute value. I mean, you actually utilize this when you're trying to prove the triangle inequality. This is based upon the definition of absolute value of a real number. And then you're like, well, I'm good to go. I know what this limit is, so we can say the limit as n tends to infinity of negative A sub n. Well, that's just a negative, so I can factor the negative. That'll be, this is so easy, you can do it in your sleep. But we were given that this limit is 0, so we basically see by factoring, we just get the negative of 0, which is 0. But we also know that that's the limit here. That is, what did we use? We used this to get that. That is, since the limit as n tends to infinity of the absolute value of A sub n by hypothesis was 0. Okay, so you're thinking, well, that's the squeeze theorem, Professor Rahn. This is always true. I mean, the cutoff point's 1, and these have the same limit as n tends to infinity, so A sub n must have the same limit. So this will imply that the limit as n tends to infinity of just plain old a sub n is 0 by squeeze. So that's really simple. Students always bellyache about proofs in calculus, and I'm often criticized about it. And ladies and gentlemen, they're simple. If you have convinced yourself that you can't do proofs, then that's on you. But the proofs that you do in calculus are based on the elements that you learned in the previous courses. And if you want to use math in a significant way, you've got to think a little bit more deeply. But look how simple this is. Now, certain proofs can be very long and arduous. I mean, there's certain proofs that are difficult, but the fundamental theorem of calculus, that should be a proof that you know how to do. That's a fundamental result from Calculus 1. And if you bellyache about having to learn that and you're in a Calculus 1 course, I don't understand that. So what I'm showing you is that even though proofs vary in difficulty and length, many are very, very straightforward, just like this one. So let's apply this result. Yeah, Professor Ron and his half sheets of paper. Well, you can tell that the glitching is less today, so Xfinity came to the rescue. It's like I say, I should be very honest. To change the plan was minimal cost. I just had to tell them what my deal was, and they were fine with it. They said, well, we've got this plan for you, and that way you don't have to worry about the speed being decreased. And I said, well, thank you. Well, I didn't really say thank you. I just read through all the notes and did it online. And then, of course, I tried to do the same with Verizon, but it wasn't as user-friendly, but that's okay. Verizon's telling me now we have 5G in the Houston area, so I need 5G, but I don't really need it, so we'll see. Okay, so here's an example that I wanted to look at here. So for instance, here we go. Let's use the last result. So prove in this particular case that the limit as n tends to infinity, or I could just say find the limit. I'm going to help you out. And of course, we're going to use some results that are intuitive, that may not have been stated explicitly. So for instance, we want to prove that the limit as 3 times sine of n divided by e to the n is actually 0. Well, this is simple if we use the last result. So now we can say 0 is less than or equal to the absolute value in this particular case of 3 times sine n divided by e to the n. But now, of course, the sine function is bounded by 1. So this will be less than or equal to 3 times 1 divided by e to the n being always positive. So this just equals 3 over e to the n. Now, again, we have a bounded function upstairs and a function that tends to infinity downstairs. So that, well, I'm just using real analysis now. I'm using a result from Cal 1 that says this is going to blow up and I'm just going to get something small divided by infinity. So this says, using Cal 1, that this limit is 0. But the limit of the absolute values using the last result is 0. So this implies the limit without the absolute values is 0. This changes sign, but it's okay. We don't have to worry about that. So the limit here is 0 by the last result. And we'll say by theorem 9.4. So even though you would look at this and say, well, you know, I know how to do that, Professor Ron. That the numerator's bounded essentially. I'm dividing by something that tends to infinity. That would be fine too. But if we want to do it, you know, without losing sleep at night, we're thinking, okay, this is the result that we just talked about. That's this result right here. if we can investigate the fact that the limit of absolute values is 0, then we get the limit of a sub n is 0. So, but the only caveat is that this is 0. If this doesn't equal 0, we don't get anything. So don't get crazy on me and think, oh, well, I've got this nice result that's applicable in any situation. No, it's not. Now, there's another result that's very useful. For instance, I'm trying to go through some examples that are useful for us, either using proofs from Cal 1 or examples from Cal 1, or just introducing an idea that's going to help us later. And here's a lemma. That is, let's fix a k. We're going to use this with Taylor's theorem. Let's fix a k in the real numbers. Then the limit as n tends to infinity of k sub n, k to the nth power divided by n factorial. Now, n factorial, remember, we define 0 factorial, at least for the 0 and the positive integers. Later, we'll be a little bit more, meticulous. This is 1, and then we say 1 factorial is 1. And then basically from here on out, we're just going to say n factorial will just be n times n minus 1 factorial. So basically, as a recursive, this is recursive, whereas this is a sequence, obviously. One element, this element depends on the previous element, so to speak. So this will imply that n factorial in general is just n times n minus 1 times n minus 2, and you just decrease to 1. So the idea here is that the n factorial function gets big really fast, and what this result is going to say is that this limit is 0. So this particular result here is very important. And again, you can look in your lecture notes. The proof is fairly straightforward, but I've got to get to some other things now. But the idea here is that when you think about it, well, heck, why not? Let's just go ahead and do it. Let me look at this result and use the last result since we can do it. So what we're going to do is we're going to take an m in the natural numbers such that, so it's a counting number, such that the absolute value of k, this fixed real number here, is less than or equal to n. And suppose, so we're going to use the result that we just proved. Suppose that n is actually bigger than m. So this is going to be able to set us up to use the theorem about absolute value. So let's do it. So now this is actually pretty simple, and we get to see how the n factorial dominates the power function, which is not a surprise. So now, a definition of absolute value, this is always non-negative. And so this equals what? The absolute value of k to the n over n factorial, which again, by definition, is non-negative. And so we're going to do a little approximation here. We're assuming that n, this natural number, is an upper bound for k. So this is m to the n, excuse me, divided by n factorial. Now, what you're thinking is we're going to show that this limit is 0, and then we can remove the absolute values and get that for free by the last result. So when I said we don't have time, well, Professor Ron's going to make time, because like, when are we going to do it otherwise? So what I want to do here is notice that this little hypothesis here allows us to move this argument forward. So what we're going to do is we're going to bump up to m factors, and then look at the remaining n minus m factors. So this equals m times m. We just keep going, and you'll see how many there are of these. And downstairs, we're just going to go up to m. So 1 times 2, all the way up to the mth factor. So n factorial is going to have a 1 times 2 times 3 times 4 up to m in it. So that means there m of these. So m factors, because they're m here, 1 up to m. And then what do we have left over? I mean, what is left over right here? Well, we've got m of these, so we're going to have n minus m's left. So let's write it down. M. I'll just put what we need here. So this is just smoke and mirrors, but important smoke and mirrors. So here we have m plus 1, m plus 2, and then the very last one is n. So now, if we look at this, and this is where we see this means what? N minus m factors, for a total of n, because we started with n. So now we're thinking we've got m to the m divided by m factorial. That's just a number. That's just a fixed number right there. I'm going to put this in yet. But notice here, this is how this is going to work and be simple. The smallest value in the denominator factor is m plus 1. So if we replace all of these with the smaller factor m plus 1, we'll get an upper bound. So this will be m to the n minus m, because we have n minus m of those. And then we're going to use the lower bound, m plus 1, to make it bigger to get an upper bound, m plus 1. Now you see what I'm doing. So we get to go over another result from analysis that we need to use here. So what we're doing here is very simple approximation. So now, when we look at this, we're thinking that's just a real number. So this is an upper bound. So notice this is a number, m to the m over m factorial. That's just a number. And then we have, use our laws of exponents, m over m plus 1 to the n minus m. Now, this is where we can use our understanding of what's going on. So now this implies that the limit as n approaches infinity of k to the n over n factorial is less than or equal to, we know this is at least greater than or equal to 0 by hypothesis. And so we factor the constant. So we get m to the m divided by n factorial times the limit as n approaches infinity of m over m plus 1 to the n minus m. Now this is where we use the fact that this number is less than 1. And our intuition, which is simple to prove, is that when you raise a number between 0 and 1 to higher and higher powers, it converges to 0. It, like, you know, you say 1/2 to the second power is 1/4. And if you keep raising it to larger and larger powers, you just get 1 over a huge number. Basically, this will converge to 0. So this will give us m, this number, m factorial, times 0, which is 0. That is, this limit is 0. Because this particular base is between 0 and 1. And that's a common result, which I will state again. We will use it over and over. So now this implies if we show that the limit of the absolute values, well, and then of course, well, what does that mean? Okay, well, that's a 0 and that's a 0 and that's in between. So it must be 0 by squeeze. But then if this limit is 0, which we just said that it is, then that means the original limit is 0 by the absolute value theorem. So this means the limit of the original sequence with no absolute values must be 0. So that absolute value theorem is very useful. The working with the absolute values is always a good thing because we get a 3 lower bound right here. And then this mechanism here is just simple algebra. But we need to say, okay, if we've got a fixed real number, we can bound its absolute value with a natural number. And then of course, to make the argument work, all we do is simply do this. What do? We do this factorization to produce a constant and then a base that's what? Between 0 and 1. So that moves the argument forward. Now, this is an ingenious argument. I actually was made familiar with this when I was an undergraduate. Of course, at the time, it seemed a little bit complex, but it's not that complex. The idea is that if you set up your system here in a way that can move the thought process forward, then you're good. That's the problem that most students encounter when they do proofs for the first time. It's like, well, I don't know what to say, or I don't know what to start with. Well, you always have to go out on a limb, just like when you're trying to solve an integral problem. First, you have to figure out what you have and what technique will work. And your first choice may just be no good, and you have to try again. So proofs are the same way. So we will use this with Taylor's theorem. This will be a huge result that we will use. And I found in the past, if I don't go over this first, then when I use it, it means nothing to my students. So boom, there we have it. Now, let's look at some other results. Now, one thing that I wanted to do here is to remind you about some simple other results that we just used. Here's a lemma. Now, the last one I did, I want you to remember, but this one, I want you to put on a note card. We'll put everything on a note card. That's what you do anyway. So for instance, if R in absolute value is less than 1, then, and we use this on the last result, then the limit as n tends to infinity of R to the n. That is, if you raise a number between, and I'm extending the result between -1 and 1, you get 0. So what's happening is that when you raise these bases that in absolute value are between 1 and 0, of course, if it's 0, that's the easiest thing in the world. But 1/2, 9/10, pi divided by pi squared or whatever, 1/pi. The limit's going to be 0. That is a fundamental result. This is fundamental, and at least it appeals to your intuition. Fundamental result. And then, of course, if we have powers with sequences, we take logarithms of them and use L'Hopital's rule like we did before. And if you don't always go back to the real variable, don't worry about it. It's probably better to do that, but if you don't, it's no big deal. I mean, if I do it, fine. If you don't, it's not going to change the result. Now, the one situation that I wanted to talk about here, let me just give you a simple case of this, so you will believe us and we'll move our thinking to the next level. That is, let's just look at one case. Let's look at case 1. What if R lived here? So we would need to do R between 0 and 1 and -1 to 0, and you can try that out. You can use the same technique I use here. So what we want to do is utilize the definition. So here we'll have, okay, well then, oh, and let me specify an epsilon and take a positive epsilon. That is, we fix this. We take a positive epsilon fixed. So this is going to work for any epsilon that you throw out that's positive. Okay, then this is how easy this is. Then, okay, we think that the limit's going to be 0. That is, as we raise R to n, and n's going to get larger and larger, we're going to be able to make R to the n close to 0. Okay, well, let's do it. So what does that say? This just says that R to the n to the absolute value is that. And then by laws of exponents, this is just R in absolute value to the n. But again, in this case, the R is positive, so we can retire the R, the absolute values. And then by definition, we want this to be less than our fixed epsilon. But now, what is this? What's a logarithm? It's a power of the base. So we can take base R logarithms of both sides. And remember, this is an increasing function, but R in this particular case is between 0 and 1, so that's a negative. So we'll say the base R logarithm of R to the n is actually greater than the base R logarithm of e. Again, remember in this case, the R is between 0 and 1, so that incorporates a negative. So you have to flip the actual inequality. So remember, this is true. Now, well, so that means that the base R logarithm is decreasing and does not preserve the inequality. And so now, if and only if, so this is just pre-cal. Bring the n down by the power rule, n. Oh, then of course, well, let me just do this in 2 steps. That's just n, right? Because we've got this, it's obvious. The base R logarithm of R is just 1, which equals n, which is greater than base R logarithm of e. So this means that we set, in this case, the big N. And again, we need a natural number. So let's do it this way. Set n element of the natural numbers such that n is bigger than this real number. And we're done. So this is the cutoff. Sometimes it's very hard to figure out an n, but this is a case where we need to know how to do it. So it is true that this is the case. And in this particular case here, when R is between 0 and 1, we can find an n. So if we take an n that is basically bigger than the base R logarithm of the epsilon that you throw out, since all of these are equivalent, it isn't true that we can make what? R to the n within epsilon of 0. So there's the proof. Once you find n, you're done. Of course, you can do another punchline, but that's just icing on the cake. I always had analysis professors at grad school in Carolina that would always have to do the punchline, and I'm thinking, okay, that's fine, but really we've solved the problem right here. Once we have an n, then we're done. We know that we can get far enough out in the sequence, and anything past that, we're going to make this R to the n with an epsilon of 0. And if we can do that, then we're done. So this is how you do that. And so what are we appealing to? Your understanding of logarithms. So the next time someone says, and you can do the case for -1 to 0, it's done the same way, just keep track of the negatives. You can prove it to them. They can say, well, you know, that seems intuitively obvious. Well, just show them using the definition of sequence limit. It's easy. You know, nothing is easy when you're unable to do it. But once you figure it out, then it's simple. And so you have to introduce yourself to the ideas. Now, there are plenty of WebAssign problems that I won't be sure to use your L'Hopital's rule if you need it. Not a problem. We know how to do that. For instance, let's just talk about some monotone situations. That's the next example. So I'll just say, be sure to use L'Hopital when necessary. That is always a useful trick. And you can do the move to the real variable or just stay in the ends, use the L'Hopital's rule and get to the punchline. Here, let's see if there's just a real simple example here that I can do with that. Say for instance, here's an example. These are easy. I don't want to insult your intelligence. It's a smart class. N approaches infinity. Say I've got n times 1/5 to the n. Okay, if we're back in Cal 1 and we have a product of two functions, or you have a product of two factors and they both go to infinity, then the answer is infinity. That's not hard to determine. That's determinate. Infinity times infinity is infinity. That's not indeterminate. But here we're looking at this and saying, well, you know, this is kind of weird looking. This is actually going to 0 and that's going to infinity. And so you're thinking, well, how do I do this, you know, in a way that's going to make sense? So you're thinking, okay, well, let me just rewrite this and maybe I can get away from this, because you don't necessarily know that 0 times infinity is 0. That's not determinate. So if we look at this, we can write it this way. We can just write 1/5 to the n as 1/5 to the n this way, and then we've got a ratio. And then this is where I'll say, okay, then you think, well, as n passes to infinity, the n gets large and the 5 to the n gets large. So this is indeterminate. So if you want, you can just say, well, let's just look at the real values. Let's do it formally. Otherwise, you could just, you know, leave that alone. But look at this. So for instance, if we have the limit as x tends to infinity of x/5 to the x, this is what I'm talking about. Later on, we won't do this, but I'm going to be formal right now. And so you're thinking infinity over infinity. So we're going to apply L'Hopital. Okay, so the derivative of x is 1. And then, of course, the derivative of 5x, that's just going to be the natural log of 5 times 5 to the x. And now we can factor the ln of 5 downstairs. And then, of course, we just have a function where the numerator is fixed and the bottom is approaching infinity. So that's just going to be 0. So that's another result from calculus 1. So we have 1/ln of 5 times 0, which is 0. The idea is we can actually work with this in terms of L'Hopital. That is, if you have something that's really huge by something that's close to 0, that's not necessarily 0. You don't know that. That's not determinate. And so you can't just, well, you can get lucky, and had you done that in this case, you would have been lucky. But the idea is that things that we look at, that's big times big is big, okay? You know, negative infinity is infinitesimally small. I mean, you know, big plus big is big. You know, those are things that are determinate. But when we don't have that, we can't just keep our fingers crossed. We have to say, okay, we've got an indeterminate case. can we rig this so we can use L'Hopital? And we see that we could here. So that's what I'm talking about. Be sure to use L'Hopital when necessary. Now, the instance that I want to speak about now has to do with monotonic sequences. And then we want to talk a little bit about infinite series. So why do we care? Let's just write this down. Now, the important thing here is the following. And I've got this summarized here that I want to show you. And I'll use my half sheet, and then we'll do an example. So this is what I want to talk about. Suppose A sub n is a sequence, and then the way I started writing this, I changed my mind how I was going to set it up, and then of course I got my white out here to make sure everything was correct. When we say monotonic, non-increasing, this covers us in two ways. When we say non-increasing, that means that as we move from the first term to the second term, we have A1 greater than or equal to A2. That is, the terms are not getting bigger. They could all be staying the same, or they could stay the same and then get smaller. We call that quote unquote decreasing, but the correct term is non-increasing. The terms aren't getting, in this case, any bigger. They could just be staying the same. So we have these inequalities here. It's a little bit weird the first time you see it. And then monotonic non-decreasing. That means in this particular case that the terms are not getting smaller. So that means A1 must be less than or equal to A2, less than or equal to A3, etc. So we call that the quote unquote increasing, even though they could just be staying the same, which is not really increasing. It's not a strict inequality. So monotonic is what we utilize when we have non-increasing, non-decreasing. When we say non-increasing, we think decreasing. When we have non-decreasing, we think increasing. Now, you might look at this and say, well, how do we actually establish this? Well, I wrote over here, you can use algebra or you can use calculus. It might be that you want to use the first derivative to do non-increasing or non-decreasing. Use the sign of the first derivative. So the one thing that makes any of this worthwhile at all is the following theorem. And it's called the monotone convergence theorem. And here's the statement of it. And I just wrote it down very simply. If A sub n is non-decreasing and bounded above. So non-decreasing, that means it may be edging up and it's bounded above. There's a ceiling, then the sequence converges. Likewise, if A sub n is non-increasing, that is, it's just, could be hovering here and then just moving down a little bit, and it's bounded below. That means there's a floor somewhere. It's going to stop the sequence. The sequence will converge. So at least in terms of intuition, this result is actually very useful. It does require the completeness axiom for the real number. So it's a little bit more advanced than we have right now, but it's not impossible to prove. The actual proof is fairly straightforward. But the idea here is that you're thinking, in some cases, I may just use common sense to get this. It may not be so abstract that I don't have to work so hard, but maybe the sequence is defined recursively and I've got to work a little bit harder. So here's the deal, everybody. You can use any calculus or algebra that you have to show that something's bounded or show that something is non-decreasing or non-increasing. Or you can be a little bit more eclectic. That is, maybe you've got a recursive sequence and you have to use some induction. So let me give you an example of this. for instance, let's do a real simple one, then I can give you one that's a little bit more complicated. So here's an example. And we don't have to use, as they say sometimes, we don't have to use anything fancy here. Say we have an a sub n equals 3n divided by n plus 2. And when we look at this, we want to show, so prove a sub n is, in this case, monotonic and bounded. Well, you can look at this and see that the limit is 3. I mean, you can just utilize the fact that, think of everything as x's, and the degree upstairs is 1, the degree downstairs is 1, and ratio of leading coefficients. That certainly works. But maybe you need to go to the next level. We need to take our thinking to the next level. So first, we can say, well, for number 1 here, we just say a sub n equals 3 times n divided by n plus 2. So we just do simpleton. So then we have 3, factor the 3, n plus 2. Again, where n is greater than or equal to 1. Well, of course, the n over n plus 2 in this case, and let me clean up the focus. As I move the papers in and out, sometimes it messes with the focus. And I know you all have really, really good eyes because you're just 5 years old, but I want it to be clear. So now, when we look at this, we're thinking, okay, well, this is less than 1. N over n plus 1 for n greater than or equal to 1 is less than 1. So we have an upper bound. So this is less than or equal to 3 times 1, which is 3. So we have a bound here. So this implies, in this particular case, well, I mean, we don't even have to have equal to. This will be strict. This will be strict. I mean, it's never going to be equal to 1. That never equals 1. So this is strict. So this says a sub n is always less than 3. So we say bounded above. Now, when you look at this, you think to yourself, okay, well, that was easy. That didn't require induction or anything fancy. It just required basic algebra and basic intuition. And then, of course, we can see that since these are all non-negative, it's also bounded below by 0. I mean, we get that for free. So, I mean, that's another simple algebraic operation that we could do because these are all positive outputs, okay? So we can do even more analysis if you like. For 2, we can look at it this way, and I'll say this. Once we do a little bit of analysis here, we can even add to what we've done here. So now let's just look at, say, f of x. I'll just go ahead and go to the real function, 3x over x plus 2, and use some calculus. And then you say, okay, well, we can do this monotonicity, so to speak, using the first derivative. So we'll factor the 3 because we're lazy. And we'll take the derivative. And so now we see the derivative here. This will be 3. And then we have what? The derivative of x is 1. So we have x plus 2 times 1 minus x times the derivative of x plus 2, which is 1. Well, this is easy. And then we get what? X plus 2 quantity squared. So now if we look at this, we see the x's absorbed, x minus x will be 0, and we're left with the 2 upstairs, and then an x plus 2 quantity squared downstairs, which gives us 6 over x plus 2 squared. This is always positive when x is greater than or equal to 1. Well, it's always positive, period. I mean, we don't even have to say that, but we're really only focusing on x greater than or equal to 1 because we have a sequence. So even though that's not saying everything, it's saying what is sufficient to do this problem. And so now we see that the derivative is always positive. This is non-decreasing. So this implies a sub n is non-decreasing. The terms must get bigger. So it's non-decreasing. They're not going to get smaller because we have a positive derivative. That means the function is increasing. Therefore, the sequence is increasing, or as in our new terminology, non-decreasing. And therefore, by monotone convergence theorem, a sub n converges. Now, we already knew what the limit was, and we wouldn't have to work very hard. I mean, this would be a rigorous proof of it. We'd say, prove that the limit is what? 3, in this case, 3. But we know the limit as n approaches infinity of 3n over n plus 2 is just what? The ratio of leading coefficients, or you could write it this way to be a little bit more formal. This will be what? 3 over 1 plus 2 over n, which will just be 3. So when you look at this and you think about this particular example, you see that we have open to us all kinds of ways to prove that something may or may, if we need to prove bounded or non-increasing, non-decreasing, whatever. One thing you can notice here is that since this is non-decreasing, observe that a sub 1, if you put in 1 here, you get 3 over 3, which is 1. A sub 2, it's going to be bigger, non-decreasing. We get 3 times 2 over 4. And this gives us what? Well, the 2's absorb, so that's going to give us what? 3/2. So now what we can see is we have a cheap lower bound. Not only, so this is going to imply that we have a lower bound. It can be equal to 1, but no smaller. And we have this, so we can even improve on that. This is a bounded sequence. And we know it has a limit point, right, due to Bolzano-Weierstrass, but that didn't matter. Monotone convergence gave us the existence of the limit. So I wanted to do a simple example so that you could actually see how you prove this. You can use induction, and I will say more about that later, but I just wanted to give you an idea of the fact that you can utilize different constructs to get to the finish line, basically what you learned in Calculus 1. So you don't have to invent any new mathematics to do this. Now, the next thing we want to do, so this is monotone convergence theorem, and you'll have some interesting problems in your WebAssign to work on, but I think you're gonna be fine with those. Now, the next step in the process is to say, okay, well, what do we do with sequences? For instance, if we have all these sequences, what would be an operation that would be useful to us? And that's called adding the terms of the sequence. So let's look at an example, how we would motivate this. So let's look at this example, or just look at the introduction of this. So again, these are all written up in your notes, but like I say, I like to summarize some things that I can use for our lecture. Let A sub n be a sequence, and we call this series and convergence. That is, we add the terms of a sequence to create a new sequence. It's called the sequence of partial sums. And you're thinking, oh, okay, so we're just gonna make it more complicated. Well, you start out with a sequence, A sub n, and you call the first term of the partial sum A sub 1. The second term of the partial sum is the sum of the first two terms of the sequence. And then you say, okay, well, S of 3 will just be the sum of the first 3 terms. And then what I've written here, the nth partial sum. And so if we're gonna call that S of n, then we have to use a new variable here for the sequence sum, because it wouldn't make any sense to have an n here and then an n up there. It'd be confusing. Even though physicists love to use and reuse the same letter, I even do it at times. And as long as the context shows you what's going on, it's fine. So basically here, the nth term of the partial sum would just be the sum of the first n terms of the given sequence. So we write that here using the sigma, the Greek symbol for summation. Now, we have the term infinite series when basically n passes to infinity. That is, if we have n equal 1 to infinity, that's called an infinite series because it's an infinite sum. And then we say, okay, if it actually has a limit, S, then we say the infinite series converges. So basically, you're thinking, I get what you're saying now. If we create this sequence of partial sums, the infinite series will converge if and only if the sequence of partial sums converges. So students always come by well, when we were actually on campus, you know, and I talked about this the first couple of years I taught at San Jac. I said, Professor Ron, what does it mean for a series to converge? I said, well, you have to look at the sequence of partial sums. I said, that's why you learn about limits of sequences first, and then you can use monotone convergence to prove that certain tests for infinite series are actually valid. So when we think about an infinite series, we're automatically thinking about the sequence of partial sums. That is, this will converge if this sequence that's generated by the partial sums converges. If this has a limit, this has the limit and it converges. And so the idea here is like you're thinking, okay, is it going to be easy to figure out the sum of an infinite series? And the answer is no. There will be cases where we'll be able to do that. But normally what we're going to want to be able to do is just realize whether or not it converges at all. And then we could always approximate the actual solution. When you study Fourier analysis, you'll be able to sum some series rather conveniently that looks like magic or whatever. So normally it won't be the case that we can always find the actual limit, but we would be able to say this series converges, and we could add up enough terms to give a decent approximation of the sum of the series. So when we think about this, the first thing we want to do, ladies and gentlemen, is look at some simple examples. And let's do a simple one. That is, right now we have to investigate the sequence of partial sums. So we're going to go back to a technique that you learned in partial fractions. So here's an example. So this is a special case. I just made this one up. So we have n equals 1, and I've already factored it. So we have 2n. It's going to remind you of that formula that we derived with the a squared minus u squared minus a squared, or flip it around, a squared minus u squared. So here's an infinite series, and what I've said here is compute sum. Now, certain special types of series are easy to work with, and they are called the telescoping. Telescoping. What that means is that the majority of the terms in the partial sum absorb. That is, they are annihilated. And so because the formula for the partial sum becomes rather simple, it usually means that taking the limit is easy. So this is a, we'll just say this is a special series. And so lots of times early on when WebAssign says compute sum, it's going to be either geometric or telescoping because you will have the means to actually figure it out. So now when you look at this, you're thinking, okay, well, maybe the way it is right now is a little bit complicated and I want to write down partial sums, and that's not going to be simple. And I can't tell that that's telescoping. So what we're going to do is use partial fractions. And of course, you know what we're going to have to do then, but let's go ahead and factor the 3. I mean, you can already probably tell me what the coefficients are going to be because this is a standard form. We'll work it out. Now, of course, this is where we have to say, well, we did this with real numbers, Professor Ron, and so we've got n's here. So we're not gonna worry about changing to x's or anything here. We'll just live on the edge, so to speak. So we'll use partial fractions. So we'll say 1. I mean, you can already tell me, you know, we had like what, 1 over 2a and negative 1 over 2a. You can tell me what they're going to be, but let's work it out. So 2n plus 1, 2n minus 1. So we'll do a over 2n plus 1 plus b over 2n minus 1. And we're relaxing a little bit. N can be, you know, other than just natural numbers. And then, of course, we'll clear denominators. So we'll get 1 equals a times 2n minus 1 plus b times 2n plus 1. Okay, so now we can just use simple values. So number 1, we'll say n equals 1/2. If n is 1/2, it annihilates the a term. So this gives us 1 equals b. And of course, 1/2 here gives us a 1 plus a 1, so we get a 2. So that, no surprise, b is 1/2. And then, of course, we can let n equal negative 1/2 because we're living on the edge, again, being flexible here. And so if that's the case, the negative 1/2 here will annihilate the b. And so we have 1 equals a, and that'll just give us what? A negative 1 minus a 1, a negative 2. So it's no surprise that a equals negative 1/2. And so now we can think about writing the actual partial sum. But first, so we can say, okay, well, here we have it. So S sub n equals the sum as k equals 1 to n. That's just the definition of partial sum that we saw on the previous sheet. And then we have what? We've got, we'll do the 1/2 first with the b. So we have 1/2 2n minus 1 minus 1/2 2n plus 1. And then, of course, the 3 right there that we factored. So this 3 here comes down. And then, of course, we can factor the 1/2. So we have 3 over 2, k equals 1 to n of 1 over 2n minus 1 minus 1 over 2n plus 1. Now, what we're seeing here is that we can see that these denominators differ by 2. And so this won't be difficult to figure out the actual telescoping bit. And you're thinking, you know, you could, at this point, the easiest way to see the telescoping is that since they only differ by 2, it's going to come out in the next, we'll see the telescoping in the first 2 terms, so to speak, because these are only separated by 2. So let's just write out a few terms. And this is how you expose the so-called telescoping. So we'll do k equal 1 Oh, and sorry, these are all K's, right? I need to make these K's. It's easy to make the N's into K's. These are all K's because now we're doing K equal 1 to N. So now we're going to spread it out. So we're going to let K equal 1. So here we've got K equal 1. So that's a 2 minus a 1. So that's a 1 minus. And then we have K equal 1. So we get a 1/3. And then we'll do K equal 2. So here you can see the telescoping already. We're going to get a 1/3 or 3 downstairs, 4 minus 1. And then a 5, 4 plus 1. So when it's only separated by 2, you see the telescoping right away. And then K equal 3. So we'll get a 6 minus 1. So we get 1/5. And then here we get a 6 plus 1, 1/7. So we see the telescoping very easily now. And let's just move on down. We'll have K equal N minus 1. So here that's going to be a -3. So we're going to get a 2N minus 3. And then here we're going to get a, so we're going to get a -2. So that'll be a 2N minus 1. So a -2 plus 1 is -1. Not difficult. I always write K, so it's easy to substitute. And then of course, this just switches the K to N. So, and then 1/2 N plus 1. So the thing is that when it's telescoping, we have to kind of show the telescoping part. We can see it here, and usually you could probably write it down if you stared at it long enough. But the first time you do this, ladies and gentlemen, it's probably better to write this out so you actually see it. So now what you see in this case is that all of these absorb. Everything goes away. That's the only surviving term. And then of course, this goes away. This gets killed by the previous one. These go away. So we see that the ones that don't absorb, this term and this term. So like I said before, when you have a telescoping sum, the majority of the terms are annihilated in sum. And that's what we deem telescoping. So now we see S of N is just 3/2 times 1 minus 1/2N plus 1. So there's a formula for the S of N, or the sequence of partial sums, which is very simple. And we know that the infinite series converges if and only if the sequence of partial sums converges. So now the limit as N passes to infinity of S of N, we can factor the 3/2. So that's the 3/2 times the limit as N passes to infinity of 1 minus 1/2N plus 1. So now we get to use the fact that we have the real calculus. Now, of course, with the N passing to infinity, we have fixed upstairs over something blowing up, and that's just going to converge to 0. Again, a very simple result from Cal 1. So we get 1 minus 0, and the actual sum is 3/2. So not only does this series converge, we know what its sum is. So that's a bonus. That's a huge bonus. So when it comes to working with infinite series, one of the simple examples, like I've written up here, special series, has to do with the fact that if we have a telescoping, then the form, excuse me, of the sequence of partial sums will be relatively simple. But we have to do a little bit of algebra. So you're thinking, if this weren't factored, it'd have to be factored. And then if you're asked to compute the sum, you're thinking, well, this must be telescoping. And if it's not, then you can't do it. So you're not going to be asked to compute the sum of a series like this unless it actually is telescoping. And so a lot of students are like, wow, Okay, so later on, we'll be able to know that this series actually converges without computing its sum, and the answer is absolutely. So you should be able, and not too far into the future, be able to determine that this actually converges without having to actually find the sum, and that'll be a relatively simple test utilizing a comparison of series. So just like the P integral, we're going to have the P series. Now, what I want to do is just talk about some simple results, excuse me, about the series. Now, one thing that I want to share with you is the following, and it's very simple. So we can kind of summarize this. When it comes to series, there are a few properties that mimic the sequences that we just did. And I wrote these out because they're very, very simple. For instance, if we have a convergent series, then we have a sum that's actually a real number. So we can suppose that the series A sub n, when we add up the terms, actually converges infinitely, in the sense that as we add the infinite number of terms, the sum approaches the real number A. And same for the sequence B sub n. As we add more and more and more terms, and you're thinking, this is crazy, Professor Ron. How can I add up a bunch of stuff and it's going to converge? You're thinking that doesn't make any sense. Well, if you think about it, what it basically means is that whatever you're adding as you get out into the sequence better start diminishing, because you're thinking arithmetic sequences don't converge. I mean, if you're adding the same amount each time, how is that ever going to converge? Well, I agree with you. So there's more going on here than just smoke and mirrors. So, and that's what's going to be addressed in this result here that's easy to prove. So you're thinking, if you sum sequences that give rise to convergent infinite series and take their differences, do you know what the result is? And the answer is yes. It's trivial. So if we take some fixed constant C and we think, okay, well, let's just dress these up a little bit, like we're doing calculus derivatives or basic limits from Cal 1. If we create a new sequence, which is C times A sub n, the result is what we expect. That is, we just multiply the limit of the series by C. So when we create a new sequence just by multiplying every term by C, we have a new series that converges, and it converges to C times A. That should not be any shock to you. That's usually how it goes with limits. But it's not an exhaustive list. We don't have a product rule or a quotient rule. Life is not that good to us. Now, if we start with two convergent series, and then we say, well, let's make a new sequence that sums sequence A sub n and B sub n. That is, we add A sub 1 to B sub 1, then A sub 2 to B sub 2. We just create this new sequence and add up all the terms. Well, does it converge? The answer is yes, and the convergent sum is actually the sum of the limits, A plus B. Now, in pre-cal, you did talk about this, but not in the infinite case, except with the geometric, and I'm sure that's probably in the dust realm right now. We need to review that. Now, the second part here just says, well, what if we create a new sequence where we say A sub n minus B sub n? Does that new series converge? Absolutely. And it's just the difference of the individual limits. So this result should not be a surprise at all, because we know that the sequence of partial sums and the infinite series are intimately related. So we should be able to, at least in these simple cases, create a new infinite series and know about their convergence. So what I wanted to do is show you a very simple proof of this. And like I say, these are so easy that they're easy just to express with some easy explanation. So what what I want to do here is look at the sequence of partial sums. So say for instance, and you can try to do 1 and 2, just do it like this. Here's the model here. So I want to just discuss this. If we want to show that this series actually converges to A minus B, let's look at the corresponding sequence of partial sums. That is, what's the partial sum for this series? Well, it would be S sub n. So we have k equals 1 to n of A sub k minus B sub k. And of course, I'm here to use the k's and not the n's. I mean, the notation will always self-correct. And then you're thinking, okay, well, let's pass to the limit. Well, let's take the limit as n approaches infinity of S sub n. Well, first, we look at this. This is just a finite sum, right? So we can break it up into 2 pieces. That is, we can sum the A sub k and we can sum the B sub k and take the difference. Okay, that's easy. And now we want to take the limit of what? 2 objects in difference that are both convergent. So that's just a sequence rule. So now the limit of a difference is the difference of limits. I mean, if this were any easier, it would be difficult. And so now we apply the limit to the first sum and we apply the limit to the second, but by hypothesis, both of these converge. The first one to A and the second one to B, and boom, we have it A minus B. So that's how simple the proof is if we just utilize the sequence of partial sums. So when students are like, well, that's so difficult. No, it's not. No, it's not. If you just kind of hang on to this definition of the sequence of partial sums, it's never going to change. And the work will be the same every time. We don't have much to work with. And this will cover us in most cases. Now, like I was saying before, we get 2 simple results here that we need to put in our back pocket and remember ad infinitum. And when I say that, if you don't get these next 2 results, then you will come to grief. And you may have already come to grief. It's like, Professor Ron, there's so much new stuff. Well, no, 75% of everything we've done today is old, ladies and gentlemen, because it's just calculus 1. So you were thinking, while I was rambling about the convergence of series, what's the key ingredient, or at least what's one of the key ingredients? If we have a convergent series, ladies and gentlemen, the generating sequence must have limit 0. Now think about that. If you are continuing to add terms of a sequence to create a sum, then whatever you're adding is going to have to get small fast enough so that whatever you're adding is basically negligible. You've done this before. What's a derivative? It's the limit of a difference quotient. Well, the numerator better get close to 0 a lot quicker than the denominator, because if it doesn't, it's indeterminate. So you've already seen this at work. And I think you kind of gloss over it because you get all those beautiful differentiation theorems and you forget about the difference quotient. And that's another situation where the numerator really has to get to 0 quicker than the denominator, or it's indeterminate. And so the beauty of the calculus is that it's so simple at times we forget that there's a lot of arithmetic going on. So it must be the case that the generating sequence here has limit 0. Why is that true? The proof is trivial. And let me show, and I want you to know this. I'm going to test you on this. I'll find some way to test you on this. If I have to do a Blackboard test, I will. I want you to know that. I want you to know every proof I've done today. Okay, we've got to move to the next level. Now, how do I do this? Okay, well, we know that the series converges, so we're going to just say its sum is A. Okay, so if we let n go to infinity, now in this particular case, and I don't even need, let me just say here, when I'm using n, I don't even have to use the k's here. I can just stick with the n's because we're not being specific about anything. So I can just write this in terms of n's. right there. We don't need the partial sum notation there. So we know that this series converges, so we're going to assign it A. So A is a fixed real number. So to the side, just say A element of R fixed. I think this is where you start to feel like a mathematician, because you're really getting into the arithmetic of things. And you're seeing how everything's just coming together in a way that's starting to make good sense. So you're thinking, okay, well, how can I rig this? This is what we want to do. We just want to take the difference of two partial sums. Let's take the nth partial sum, which is this, and let's take the n minus first partial sum, which is this. Now, if I take the difference of these two sums, all the terms from one of the n minus one absorb, and this one holds on to the a sub n when k is equal to n, and that does not get absorbed here because that only sends to n minus one. So a sub n is just the difference of these two partial sums. You're thinking, how fortuitous. You're thinking, wow, Professor Ron, that opens the door to illumination. Okay, now you're thinking, well, Professor Ron, that does it. We have a sub n is the difference of two sequences, and we know these sequences both have limit a. And what's a minus a? Well, it's 0. So applying the limit, we have the limit as n tends to infinity of a sub n is just the limit of this difference. But that's the limit of s sub n. Well, I mean, heck, if you're adding the first n sub 1 terms or n minus 1 and n terms, it doesn't matter. N is marching off to infinity. Both of these limits by hypothesis are a, and a minus a is 0. So the limit of the generating sequence is indeed 0. So this is one of the simplest proofs ever, but a proof that will confound you if you don't think about the partial sum. So when you think about an infinite series, the first thing that should click on in your brain is the sequence of partial sums, because that will always be the way that we have to analyze what's going on. Now, we can't do every proof, and there wouldn't be time to do every proof, but we're going to do enough of them so that you get a basic understanding. Now, of course, here's the beauty of this result. Now this is what's very important. Just because a generating sequence has limit 0 doesn't say anything about convergence, so that is untrue. However, if we take the contrapositive of this, remember, when you're dealing with implications, P implies Q is equivalent to the contrapositive. That is, not Q implies not P. That's the contrapositive. Contrapositive. These are logically equivalent. Here's the conditional, which is how we state our theorems. So here's what we do. We take this if then, flip it around and negate it. That's what the little tilde means. That means negate. So we're going to say this limit is not equal to 0, then this must diverge. That's it. We get a free theorem due to logic. So what this basically says, if someone says, or a WebAssign says, okay, determine whether or not the series converges or diverges, or prove that the series diverges or whatever. Before you do anything, you can say, okay, wait a minute. If I look back up at this one here, and you look at the generating sequence here, right here, as n goes to infinity, that clearly is 0. That doesn't tell me that this series converges, okay? But at least I know I can investigate more. I need to try something else. Now, if you're looking at a series and you're thinking, well, I need to use a convergence test. If you check the generating sequence and it doesn't have limit 0, then you're done. You know it diverges, because that is the contrapositive of this result. So if you're thinking, what's the sum of the series of n equal 1 to infinity of n squared. Well, that's diverges clearly. N squared doesn't converge to 0. It blows up to infinity. So the thing is, do yourself a favor and really put this in the toolbox in the sense that if the generating sequence doesn't converge to 0, there's no hope for convergence. Even when it does, doesn't mean that the series converges. It just means that there's a reason to look a little bit more into some detail. And as we actually develop more and more results, we'll have nice examples of divergent series and nice examples of convergent series that will help us to compare infinite series. So remember, what we'll do tomorrow or on Wednesday, we'll talk about geometric series to finish this up, and then we'll talk about the integral test. So again, as you're leaving today and you start working on your homework and things like this, just remember that these two theorems come as a pair, and they give you plenty of room to work. Again, never use the fact that the generating sequence converges to 0 to conclude that the series converges. That is patently false. But if the generating sequence has a non-zero limit, then you are done. So you need to master the concept here. Not mastering this or anything that we've talked about today will put grief on you. So even though this is simple, it's kind of like learning the unit circle for the first time. If you don't learn the symmetry of the unit circle and master what it means to compute a reference number, then the circle is abstract to you. So take all these basic ideas that we have here and utilize them. Now what we'll do, we'll talk about the geometric sequence or series and all next class, do an example of that, and then we'll talk about the integral test. So if you want to go ahead and read ahead, you're welcome to do that. Thank you for your attendance today. This material will be fun. We will do some integrals in this part, but a lot of arithmetic, and this will prepare you for great things to come when you get into your more advanced physics classes and engineering classes, and of course, differential equations and partial differential equations. Okay, everybody have a great day. Thank you for your attendance.